Okay, I was in Munich, and I came home late Sunday, so I couldn't lecture on Thursday. I was getting an award. If you want to read about the award, you should look at the web page of the Berkeley Astronomy Department. I'm on the front page. Okay. We're going to finish off discussion of stars today, and we're going to talk about the stars that make gold, which is very important to us. We need gold for money, basis of money. We need uranium and all the other stuff. And one question is, where the hell does this come from? It was a long time. Scientists thought that maybe it was made in the Big Bang, right at the beginning. Maybe it was left over from the last cycle of the universe that had a big crunch and then a big bang. All those are suppositions turn out to be wrong. But we finally came up with an idea that works to explain how you get heavier elements, how you get most elements at all. This was only worked out in the late 40s. So that is 1950. This was understood. All right, today we're going to talk about what does all that. And what does it is something like this. That is a supernova, a star which quietly, or not so quietly, was dim for a while and then suddenly became incredibly bright, 1 million times brighter than usual, and it was exploding. So we wanted to understand, a very important question for astrophysics is understanding what in the hell is making this thing explode? How does this work? Now, these are not very common events. There was one in the year 1054. There was another during Kepler's lifetime. And then there was one in 2003, I think. No, I don't remember. Maybe 1993 in the Magellanic Clouds. They're very, very rare. So what is that makes the stars go bang? All right. Hello. It's supposed to flicker. Just a moment. Okay. All right. Let's see what happens. Okay. Now, what happens is the following. You have two stars orbiting each other, and one will go first. The heavier one will, as is expected, it will end the main sequence lifetime sooner. So then something will happen. So let's see what happens. Now one star, there it went, exploded, and it became a lighter star, but it had with it, had the binary star, which now grew, and then starts to spill over its region, spill over the mass. And what it is doing is feeding. Let's see if I can stop. All right. So what's happening is the events are the following. The faint star, first of all, the blue star, first of all, goes into the end of its lifetime. All right, it blows all the stuff off, and it ends up being a white dwarf star. Just blows it all away. And that's more or less what the sun will do in 5 billion years. But we know if it's a blue star that the process will happen faster. Then, over time, the red star will get larger and become a giant star. When it becomes a giant star, it becomes something, it fills something known as the Roche lobe at the Roche. What it does is it becomes so big that it wants to be larger than say, this radius. And at that point, an atom there says, well, I think I'll just as soon fall to that star. And it forms a stream, a narrow stream of material. So that's the stream you're going to see. So let me play this again. So the one star blew up. The other star now has moved off the main sequence, and it has a stream of material coming down onto the white dwarf, and heats it up. Heats it up and heats it up and heats it up. It keeps pouring material onto it. So the material eventually exceeds the Chandrasekhar limit of 1.4 solar masses. So it just keeps going, going, and going. And the stream will eventually exceed anything. So this star is feeding the other one. Note that the binary system did not dissolve when it blew up because it retained most of the mass it had before. So the star will just continue to accrete. All right, now what does this do? This is a common occurrence because so many stars in our galaxy are binaries. All right, so this will happen whenever a binary star evolves off the main sequence. Okay. Okay. Now, what happens is the following. The star, it becomes a nova. It's called a nova. A nova is a new star, new. And this is a new star because these nova were first seen by Kepler and by Copernicus. And this is antithetical to the notion that the starry heavens are fixed, because here was a star that became visible. Suddenly it was there, it was nothing, and then it becomes visible. At least they couldn't see it before. And then it becomes visible, and then it fades. What is that? That can't be a starry heaven. It's not perfect. It's changing with time. So what has happened is that the star, a companion star, is exceeding its Roche lobe and moving its pouring material from there onto the white dwarf. Eventually, a nova occurs when the shell becomes big enough to exceed the white dwarf limit. Now, you talked last time about the mass limit of white dwarf stars. That was the work of Chandrasekhar. What happens to make a star go beyond the white dwarf limit? What is going on? Well, that's one thing. Yes, that is what happens in a nova. You're right. Okay? So the hydrogen and helium on the star, the nova star, is pulled in by the gravitational attraction. It's quite massive, quite a thick coat, not really thick, it's only meters thick, and very dense, and then it goes and starts nuclear fusion on the surface. So it just literally blows up. Now what it's doing is blowing the material off the shell. Okay, so the shell contains a very, very small amount of mass. It has accreted for a while, but it has accreted a tiny mass. It's 10 part in 10,000 of the mass that was there. Okay. And you cause the white dwarf brightens by 10 magnitudes. Brightens by 100,000 in a few days. So that is quite a brightening. Okay. So those are called novae. Now, because so little mass, the explosion does not disrupt the binary. The binary system stays together. The mass is a small perturbation. Okay, ignition can occur again and again and again because the feeding star continues to feed it. And as it accumulates material, it'll blow up again and again and again. Okay, and here is the result. This is a nova. That is basically a white dwarf, and here's all the material that is scattered around it. This is taken from the Hubble Space Telescope. Okay, so this is the sort of thing that happens, and this is fairly common. Okay, now that's just an ordinary star. An ordinary star in a binary. Now let's look at another case. Okay. Now, let me see that. Is this really? All right. So what is happening in a heavy star is that it has burned through all the material it can. It burns the hydrogen, the helium, and then hydrogen is on the outside here, the white layers of hydrogen here. Then there's a layer that burns helium to carbon through the process we talked about. Then carbon absorbs another alpha particle, becomes oxygen. Oxygen absorbs more, and it becomes magnesium, I think. And then another one, and it becomes silicon. And eventually it absorbs material and becomes iron in the center. Now, iron is something that is as heavy, it is something that won't gain energy either by absorbing or emitting photons, or, either by absorbing or emitting neutrons or alpha particles, which is a part of helium, remember. Remember, an alpha particle is 2 neutrons, 2 protons together. And that's helium, helium-4. Okay, so what happens in the high-mass star? And this star is much heavier than the mass of the Earth, than the mass of the Sun. Okay, so wait a minute. I'm going to, damn it, how can I go back to the beginning? Oh, all right, here we go. All right, here's a better, all right, let's start earlier. Now, there's a hydrogen burning shell, there's a helium burning shell, and an inert carbon core. This is about how far the stellar evolution will get in our sun. All right? So let's take this to be an ordinary star, a heavy star that's ending its lifetime. So if we begin, it will burn. Here's the star on the outside. It will burn until you have carbon burning in the center. And you end up getting carbon burning. It burns out quickly. And then you have oxygen in the center, surrounded by helium out here, surrounded by hydrogen out here. All of them are burning, except for the oxygen in the core. Why isn't that burning? Well, it's not so far, the temperature is not high enough for the alpha particle to overcome the repulsive barrier to the oxygen. So it's going to have to get hotter. How does the star get hotter? It does it the way it's done before. It gets hotter when the burning stops, or stops when it's out of fuel, and eventually it shrinks. Is the pressure, the overpressure is too high, the pressure in exceeds the pressure, the force in of gravity exceeds the pressure outward of the star makes. So the star naturally shrinks. And as the star shrinks, it heats up. This is the thing that's so unusual. The star heats up as it compresses. That's what is completely different from ordinary material, like ember of coal. Ember of coal, as the coal stops burning and giving off heat, the coal has no tendency to shrink. But in a self-gravitating ball, it does have a tendency to shrink. Self-gravitating balls are very unusual to your way of thinking. They do not follow your intuition. Or I should say your intuition is wrong. Okay? The star will shrink as it runs out of energy. It runs out of energy is the same as running the ember until it burns out. But it doesn't shrink anyhow. All right, so you've got an inert iron core. Now, you know that as we squeeze the star further, it's going to burn the iron, or burn the oxygen. All right, we have an inert oxygen core that will burn if you squeeze it. So let's continue. The star ages a little more, and we have non-burning hydrogen, hydrogen fusion. This out here is the area that's non-burning. Here's the burning hydrogen, burning helium, burning carbon, carbon fusion. Where the heck did I say? Helium fusion is up here. Okay, so layer by layer, the star is burning. It's burning the easiest thing it can at that layer. But eventually, the layer runs out of fuel, and it will burn more as it squeezes further. So that's what the star does. All right, so let's do this again. A little bit more. The star is swelling, pulsing around. All right, then it becomes eventually magnesium, silicon, iron. And so we suddenly find a star that it's a real layer cake. The star is crazily all these mixed up layers. Now, two things. One, the star, the Earth, the sun is very different from this. It does only one region of burning, and that's in the core. But these stars, these heavier stars at an advanced stage, get this very complicated structure. Now, it's drawn spherically symmetric, but it probably is not spherically symmetric. It's going to be a little bit jumbled up. And so this is just to give you an idea of what happens. So anyhow, you have each of these elements, carbon to oxygen to neon to magnesium to silicon to iron, they all differ in the nuclei by 2 protons and 2 neutrons. That is the step difference between them. And that is the addition of one helium atom or alpha particle. That's how they make that step this way. So you skipped over a lot of elements. Fluorine, neon, neon's there, all these other things. But all these other elements are skipped. Somebody must know all the elements. Who knows the elements of the periodic table? Here, between helium and carbon, there's beryllium, lithium. They're not here. Very rare. They're rare elements in the center of a star like this. They're skipped. And then between carbon and oxygen, what's the element between them? Oxygen is 8, carbon is 6, fluorine is 7, I think, isn't it? Anybody know? No, oh gosh, nitrogen. Yes, right. That's a. Okay, thank you. All right, so these other elements they're simply not there at this time because they differ one to the next by an alpha particle, which is in the center of the stars. Alpha particles can be existing. All right, so you have this iron core is what is in the center of a star. Now, the evolution is moving fast. It'll take just a day or two for the star to move to burning iron core until something else happens. It does not take a long time. This is the end of a star. It's taking longer for me to talk about it than for it to happen. All right. So now, let us go further. Let's talk about the next step. All right, so the star is going to die right now. Here's the size of it. Now we're going to first we're first going to back away from the star. All right, so it's going to back away. Fusion of iron will not give off energy. What the heck happened? The star blew up. Suddenly, it just blew up and became a spectacular supernova. And it's like a nova, only superb, really big. It is much more powerful than a nova. And what did this? This was a big mystery. This is what was seen at the spot of the sky where the 1054 supernova occurred. For some reason, that supernova was not recorded in the West, probably because religion did not allow the sky to change, so they didn't record it. It was a very bright event. You would have seen it. It was, believe it or not, the supernova was as bright as the full moon, all pointing at a star. You could not miss it. The Indians in the West, American Indians, Western Indians, have recorded it if something happened. In the Chinese court, it was recorded as well. But the Western scientists, or theologians at that point, didn't record the event anywhere in the West, which was crazy. They certainly saw it. You have a question? Okay, this event occurred in 1054, and it blew up. We'll see this later. This is called the Crab Nebula. It is an expanding ball of gas, and all these heavy elements made in the supernova. Guess what? The supernova is responsible for all the heavy elements that we are made of. It's responsible for the gold in my watch, my watch, and the gold in this ring. How did that happen? Okay. So come on. Just a second. Okay. So all right, so what happens? Let us talk first of all about white dwarf supernova. That is a supernova not of a massive star, but it's a supernova made of a white dwarf that's been accreting material. What can happen? All right, if the accretion brings the mass above the Chandrasekhar limit, then what will happen to the star? Chandrasekhar said, well, the star will collapse. That is the upper limit to the mass of the star. His advisor, he came to England to work with Eddington. He was on a ship from India, coming to England. He worked out all this on the ship, but he showed it to Eddington, who laughed, and he said, "This is ridiculous," and ejected him from the office. But Eddington was wrong. All right, what he said is that as a star exceeds the Chandrasekhar limit, which is 1.4 solar masses, then electron degeneracy is not sufficient to hold the star up. Remember, electron degeneracy is the electrons bouncing around when the space for them is too small. It's like the chairs removed from a lecture hall. All right, so the electron degeneracy is gone. And the white dwarf collapses. All right, so the collapse raises the core temperature, and the star was carbon inside. It was a carbon, oxygen, white dwarf. But this carbon suddenly is all of a sudden going to fuse easily. Remember, the electrons have disappeared? Well, what happens to the electrons, first of all? When I say they've disappeared, I haven't explained myself. The electron pressure is no longer holding the star up. And so let's say, just for a moment, the electron pressure is not strong enough to hold the star up, and that means it will collapse for the gravity that was balancing the star. It was in equilibrium, thermal equilibrium, but suddenly it is not. The planet has been accreting material, and suddenly it exceeds the Chandrasekhar limit. All right, so then it collapses. What's going to happen is that the temperature is going to really climb. It climbs extremely fast because there's nothing. It just has nothing to stop it. And it climbs and climbs and climbs, and the carbon starts burning, and it burns furiously. Furiously. Okay. All right. It will collapse and ultimately lead to an explosion, and the explosion is known as a supernova, a white dwarf supernova. Now, this is called type 1 supernova. We're going to talk next about a different type of supernova. So this is a type 1 supernova. Okay. What does it look like? All right. Remember, first we talked about a nova star when the hydrogen layer on the outer portion of the star flashed. It burned very quickly and reached a luminosity of 100,000 times that of the star. But this thing is a monster. This it'll attain a luminosity of 10 billion times this luminosity of the sun. That is this is 10 to the 5th, 10 to the 10th, this is 10 billion, and that means it's a luminosity of 10 to the 10th, that of the star. That is really bright. Okay, they're all attained, more or less, almost all supernova attain the same peak luminosity. That makes them very handy as a distance indicator, as we'll see later in the course. These are so bright, they flash, and suddenly you can see them all the way across the universe. And that is really bright. It's like somewhere in the universe, what you're going to do is say, well, okay, it's like a flash bulb turning on somewhere. If you happen to know how bright the flash bulb is, or how bright the flash bulb is compared to another, you can tell how far away the object is, because the luminosity falls as the distance squared, and the further away it is, the brightness you see falls as the square of the distance, and the further away the supernova is, the fainter it'll look. So a lot of work has been done on the Hubble Space Telescope and other telescopes to find supernovae. Why? We'll talk about that later in the course. All right. So these can measure incredible distances, way further than you can see the distance to Cepheids or almost anything. All right, and again, there are two types of supernova. There's what we've talked about, a white dwarf star. It doesn't have any hydrogen because the hydrogen is all burned up on a white dwarf. There's no hydrogen left on the star. And what blows up is all heavy elements. You can also have a massive star go into a massive star that has iron in the center. That will eventually make a supernova, as we'll talk about now. And this was called type 2 supernova. So type 2 is heavy stars that make elements, make a lot of elements. Type 1 is a white dwarf star that exceeds its Chandrasekhar mass limit. Okay, now, so the star exists. Now, the problem is that if you talk about the mass per nucleon, let us label here atomic mass number, atomic mass. It goes from hydrogen to uranium. Now, let's see what we have. Okay. Supergiant has, if we're talking about the iron core problem in a massive star, it has iron core, and the iron core cannot be fused. It cannot be fissioned. Iron cannot give off energy by releasing anything. If it fissions, it could move that way. Fuses move this way. But both of them take energy. It's an energy loss to do anything to the nucleus. This is the excess energy, the mass per nuclear particle. So hydrogen atom goes up, and converting hydrogen to helium, it has quite a bit of energy. This isn't really clear what that is. This is energy that you can release. So we got a lot of energy out of the star when we burned up all the hydrogen into helium. The star gets a little energy when it burns to carbon, a little bit when the carbon burns to oxygen, and eventually burns to iron. The first stage is the stage that lasts a while because of fuel. You've got fuel that really burns for a while. But after then, the star burns very rapidly. Okay. All right. Now, the iron core is going to shrink and shrink and shrink, and then what's going to hold up the iron is electron degeneracy, more or less the same that's holding up the center of a white dwarf. The electron degeneracy will apply to the iron core as well as it applied to the carbon core holding up the white dwarf. So the iron degeneracy keeps it from collapsing. You've got to have something there or the star will collapse. All right, so what happens in the center of a star, a big star, is eventually there's something called an iron catastrophe. It's really amazing what goes on. All right, so the degenerate core is continuously building in mass, and finally reaches the Chandrasekhar limit, 1.4 solar masses, just like in the white dwarf. This is now in the center of a star. Remember, a white dwarf has thrown all the junk away from the star. This is just a light. It's an object of just the solar mass. This is in the center of a massive star, say 8 solar masses, and it still has the envelope of other material on top of it. So it will, again, exceed the 1.4 solar masses. What's it going to do then? All right, the temperature reaches 10 billion degrees in the center of the star. A crazy high temperature. Unbelievably high. What does it do? What's going to happen is the nuclei will get broken by the nuclei are slamming around in the center of the star, and they're so energetic that if 2 iron nuclei hit each other, they'll break up. Now, how can they break up? It takes energy to break it up. But if you've got enough energy with the photons and thermal motion, that's fine. There's plenty of energy in that. And so it breaks up. All right. It takes a lot of energy. All right. It takes plenty of energy to break up the iron. And so it's going to drain from the core. This is going to lower the pressure, causing the core to shrink and to heat up. So the core, by radiating, by photodissociating, the star has a lower pressure, and that means the gravitational force pushes on it. Now you see, this is incredible. Gravity sucks, pulls the star together, pulls it together constantly. It will not give up. All right. So now recall what happens in the degeneracy. Suppose your energy is so high that you get in a reaction that goes like this. Electron plus a proton goes to neutron plus neutrino. Now, you know that won't go in the laboratory. If you just take a pure neutron and you have a bunch of neutrons sitting in the laboratory, then the reaction occurs in reverse. This reaction, a neutron will decay to a proton, electron, and neutrino. All right? That's the way it goes. But if the energy is high enough, you can make the reaction go backwards. Now, what type of reaction is that called? Endothermic versus exothermic from chemistry? Who knows the term? Did you? You took chemistry. Some of you did. Who's the chemist here? None of you took chemistry, but you said you did. You took it in high school. Huh? This reaction is exothermic. Okay? But this reaction is endothermic. Right? This takes energy to make it happen. This one gives off energy when it occurs. So the star blows, what has happened here is really kind of interesting. The electrons were providing the pressure holding the star up. And now it becomes energetically favorable for them to disappear. They combine with protons to make neutrons. That's neat. So everything that was holding the star up disappears. In other words, you pull the plug on the iron core. All of a sudden, there's nothing providing pressure. It was sort of providing enough pressure to keep it up, but it was shrinking, and now there's nothing. So what happens? Well, you haven't got anything. You still got gravity, and it just pulls it together incredibly fast. The whole thing, we're talking about something with reaction, the whole thing is over in 1 second. But what happens in that 1 second? All right. The result, as I said, the electrons are all disappear. They merge with protons, and the plug is pulled. It's like you're in a bath that's full, and you reach down there and pull the plug, and the water disappears. Here the water disappears. I mean, the center of the thing just is gone. So what does that do? All right, the star, this is a very, very short time, just a few milliseconds. And what's going to happen, you've converted all the material into neutrons. The neutrons are there, and you can keep them there, and you call the result a neutron star. It is a very compact object, neutron star. That is an entire star made out of neutrons. There are very few protons in it. That is a neutron star. And that's either going to form or it might become a black hole. And that is the next stage beyond a neutron star. Yes? Why are they hot? Well, you just went through a reaction like this. It would be hot too. I mean, you've been compressed and heated and jostled around. It has so much heat when it's born. Now that heat will eventually dissipate and go away. But until then, it's very hot. Yes?
Can we, in a controlled environment,
Well, electron from a neutron, sure. Well, if you have a batch of neutrons, and they won't respond to an electric field, but the electrons will. So just hold a plus region here, all right, and electrons will be attracted to it. They're, after all, negatively charged. They'll just drift that way. How's that? Or you make this side, make the field, the electric field, point in a direction. You do it with a battery. Here's one pole of the battery. Here's the other. You have an electric field across the entire region. It'll pull the electrons out. Oh, trivial. I mean, first of all, you can never get close enough to these conditions on the Earth. It's 100 billion degrees. I mean, there's no material that'll hold that. And the densities are impossibly high. So you just can't do it. All right? It'd be nice if you could, I suppose. Actually, no, I take it back. You can do this. Not this extreme, but you can do it partly by a hydrogen bomb. Right in the middle of the hydrogen bomb, the densities are unbelievably high, and it blows up. Why does the hydrogen bomb blow up again? Anybody? Why is the hydrogen bomb different from the star? Sorry? No gravity pushing back on. That's the difference. The star has the entire mass of the star pulling it together. The hydrogen bombs, and there's a lot of hydrogen bombs equivalent there, cannot pull it apart. It's not strong enough. Okay, so you've had fun time doing that. All right, the neutron star, at this point, the star has incredible density. We estimate the density is 10 to the 12 grams, and 10 to 12 grams per cubic centimeter, and that's a factor of 100 or so higher than the density of neutrons and protons together when they're in a nucleus. You're making this star heavier or denser than ordinary nucleus. You can't just take nuclei and put them together. They are not a neutron star. So you push them together. So it's going to, equilibrium density is 10 to 12 grams per cubic centimeter, I'm sorry. But when the neutron star forms, it's going to push up to a density of 10 to the 14th or 15th times that it's going to be 100 to 1,000 times denser than that of a nucleus. It gets very, very dense. And the star is going to bounce. You squeeze it really hard, a neutron star squeezes, and then it bounces. What's it going to do with the bounce? Well, the star, the material making the star, has fallen in really at a high speed. The speeds are approaching the speed of light. They're slamming together, and then they bounce away. That means it's coming with tremendous force on the material on the outside. So all the material outside the core has suddenly a heavy bounce applied to it. And it makes it turn around and blow apart. So suddenly, you've got everything in the star just blown up by the generation of the neutron star. The neutron star manages to pack a wallop and push all the material away from it. All right, so what it'll do is, all right, the supernova has taken a neutron and a proton, combined them to a neutron and a proton into, combined a proton and an electron into a neutron and neutrino. The neutrino is a particle that I said is very, very capable of flying away. But in this case, the density of the material around the neutrons, around the core of the neutron star, is so high that finally the neutrinos are trapped. And they do not have enough energy and they don't have enough energy to get out, and the cross-section is too large, and they will be stuck there. But they're going to hit the outer star with force. All right, the force of gravity increases. Gravity has overcome the electron degeneracy. Electrons have smashed the protons and neutrons. Neutrons would have decayed if they were at room temperature and pressure, but they don't. The core collapses to form a neutron star. The neutron star collapses, stopped by neutron degeneracy. The core recoils and sends the star flying into space. It gets pretty complicated. This is all very complicated. At least this is what we think happens. This is according to the best computer simulations you can do with this subject. It's very difficult to do these calculations. And they are the subject of much current research. A lot of people work on them. All right, so what's going to go on? This is a type 2 supernova. All right, now the creation of each neutron has released one neutrino. And the neutrino flows out of the star, but the star is so dense, they will interact with the core regions of the star. They're hitting it, and they have their momentum that pushes on the star, at least for a moment. Okay. The rebound of these neutron stars and the momentum from the neutrinos is enough to reverse the collapse of the material that is falling in. At least we think that's what happens. We're not absolutely certain of that, but that's what the best bet as to what happens. Okay. And so what you see is it blows the star apart, and the star blows up at an incredibly high velocity. 10,000 kilometers a second is the velocity of the expanding star. That's the velocity of the Crab Nebula. If you look at the Crab Nebula and you measure the velocity of the filaments outside of it, they're moving at very high speed, very high speed. Okay. Now, the interesting thing is that the energy of the outgoing material is not carried by the exploded material. All that junk that's blown off only carries 1% of the mass of the energy of the material. 99% of the energy of the material is carried by the neutrinos. These are the ghostly particles that you can't see very well. The neutrinos can detect this. Neutrinos exhibit incredible smash of, they exhibit a huge burst, and they're carrying the energy that happens when you released when an electron and proton converted to a neutron and neutrino. Now note the neutrino is not an optional ingredient. The neutrino has to be there because this is a weak interaction. If you have an electron, you have to have a neutrino on the other side of the equation. So the neutrinos are created with tremendous energy, and it's enough energy to carry 99% of it. Okay, the supernova is known as type 2, and it is about as bright as the supernova of type 1. These events last about 50 days. Okay, the last close-by event occurred in 1987 in a nearby galaxy known as the Magellanic Cloud. It's 55 kiloparsecs distance. This was a very, very exciting time in Berkeley and all around the world. We had a supernova, a live supernova. First time in recorded history that we actually had something that we could study. Okay, this is the first time. This is an amazing event. The neutrinos which carry 99% of the energy, and I told you they can flow through you and don't interact with you, we actually detected, what was that? 18 neutrinos were detected in a 15-second interval. 18 neutrinos. This was by 2 separate experiments. There was one in a Japanese experiment. That was the big, remember the experiment I showed you that showed men in a rowboat it's a big lake. It was underground. That's called Kamiokande in Japan. And that detected neutrinos. This is a huge event. I mean, a huge water chamber. Now, that was one detector. Another detector was buried under a salt mine under Lake Erie. I've forgotten what it's called. But it detected neutrinos as well. Both of them saw this. And they saw it 15 seconds after the first burst of the neutrino was detected. We actually saw when the burst occurred. And just before that, very shortly after that, 15 seconds later, these neutrino emissions were detected on the Earth. Yes? Well, it's not that they don't interact with anything. It's just that their cross-sections, their probability of interacting with anything is really pathetic. They can go through you and not interact with you. But if you take a water tank that's really huge, I mean, it's much more than a swimming pool, really big, it'll hit a few atoms in there. Now the question is, how do you ever detect something in that? It's incredibly ingenious. The other thing was the tank of cleaning fluid that was in a mine that I told you about. Okay, that tank of cleaning fluid was another way to detect them, because an electron would come in, and neutrino would come in and interact with a atom of chlorine that's very abundant there. The chlorine would convert to argon, and the argon could be detected because they would filter it. They'd filter this thing with a pump, and they trap the argon. It's amazing they could do this. A tiny bit of argon is trapped as it filters through, and they detect it. The argon was stable for only a few days. It would then radioactively decay, and they had the counters around the trapping, and after a few days, few weeks, they would see all the argon is detected, and it's there. That's all they could do. It's astounding that was done. That is a feat of chemistry. Amazing piece of chemistry to do this on a huge tank of cleaning fluid. Okay, so this thing saw the event. It was quite astounding. All right, these are roughly, they occur roughly about 1 per 100 years. This team, you can discover them by looking at a lot of galaxies. There's 1 per 100 years in our galaxy, but suppose you look at 1,000 galaxies or 10,000 galaxies. You have a telescope that points, takes a picture, points, takes a picture, points. It goes around the sky. It knows where there's a bunch of satellites. It automatically goes one after the other, after the other, after the other, taking pictures every night. And you're looking for supernova. You're looking for bright flashes. This is a project that is done by Alex Filipenko in our department. He had a lot of, I don't think he has this anymore, but he had a lot of undergraduates like you who would look at the plates. Not the plates, they would look over the data. They have an algorithm that looks for the differences of the galaxy with with the same galaxy taken earlier when there was no supernova, and they just compared them. Keep comparing galaxy by galaxy by galaxy. This is, after all, what computers are good for. You know, just go through this, and it would flag events that it thought might be a supernova. people would then look at it and either confirm or deny is a supernova event. It's pretty neat. And by that means, he discovered 100 per year. It's a slick way to do it. All right, so let me tell you about the Large Magellanic Cloud event in 1987. There it is. This is the Magellanic Cloud. This is only visible if you're in the southern hemisphere. This is the Cloud of Magellan. It's the big one. It's a nearby galaxy. All right, and here's a supernova event. All right, you can tell which are the supernova in these pictures because they have the arrows. See, the star with the arrow is a supernova. That's the way to tell. Okay, and here's what it looks like now. Beautiful. Here's a supernova event, and it blew off a ring and then another ring before it. It wasn't spherically symmetric. It blew this material off and made these rings in the sky. That's the supernova event. These rings are all recent. I believe this ring was material from the star that blew off the star before the supernova event. The star was coughing, and it just threw off this junk, this hydrogen and helium on the outer star. Supernova event occurred anyhow. All right, and this is Kamiokande. This is the giant detector that saw the 18 neutrinos, and it occurred 15 seconds later. Question? These are people working. I'm sorry, I've got this a little bit screwed up. But these are light detectors, and these people are checking something. I don't know what they're checking. Just putting it together. All right? When it's working, the whole chamber is filled with water. Okay? That's a device that saw these neutrinos. This is the first time neutrinos had ever been detected by an astronomical tool. Actually, not the first time, but this was a big time. Okay. Now, here are events. This is the event. What's this one? Oh, shoot. I can't see what this is. Hang on a second. Okay. All right. This is another supernova event. This is a different supernova that was captured. It was seen by the Hubble Space Telescope, and this shows the event in different days. In May, in September, October, December, and this star had blew up and ejected material from the outer envelope. And the material really is moving very fast. This material, you can just measure how fast it's moving by the angular diameter growth, and it's moving 10,000 kilometers per second, typically. It's really incredible. This is a supernova event of one star. This is a beautiful detection. All right, so here, this is a supernova on this galaxy. They're as bright as the entire galaxy. Astounding. Okay, now, here's a picture that shows the evolution, the summary of the evolution of these stars. And the evolution Okay, here's an example of what we think happens. A star that's born with more than 25 solar masses we'll put in this category. It first starts off as a protostar. As before, it forms a star. It forms a star which is destined to become a bright blue star. 25 solar masses is heavy. Becomes a supernova event, supergiant, supernova event, and eventually we think in that case it forms a black hole. Does not form a neutron star. The candidates that are probably the most likely to form a neutron star is something that was born with 8 to 25 solar masses. It went through the evolution, giant, supergiant phase, then blows up into a supernova, leaves a neutron star. So it had a lot of mass. 8 to 25 solar masses is quite a bit. A lot heavier than the sun. Okay, if you then, another supernova, another event, if you have a 4/10 solar mass up to 8 solar masses, becomes a giant, a red giant, then planetary nebula, and then eventually becomes a white dwarf. All right, so these stars are a little too light to become an exploded neutron star. A neutron star has to be, to become a supernova, the star needs to exceed 8 solar masses. Then it can blow up by itself. All right. If they're between 8 and 4/10 solar mass, it'll just burn. Nothing will happen. With less than 8/100 of a solar mass, it doesn't burn at all, and it's known as a brown dwarf. So these stars, if it's a light star, nothing ever happens to it in the lifetime of our entire universe. They just sit there. If they get heavier, as they get heavier, they will go through more and more evolution. Some of the stars, the heaviest stars never go very far. They don't go into the giant branch at all. They start off as supergiants and blow up from that state. Go directly to what we think is a black hole. Now, these stars aren't very common. Stars that are, stars are born in a big cloud, and there's typically a lot of the light stars and very, very few of the very big stars. Probably 1% of the mass of the whole cloud, the 1% of the stars that form, 1% of the mass of them forms into material that is suitable to make supernovae. The rest of them don't. So these are very rare events. Okay. Now, but they're extremely important for us. Okay, first of all, let's finish the supernovae. All right. Now, the first broad category of supernovae is this type 1. All right. Nothing hydrogen-like in the spectrum. And type 2 is these are the white dwarf supernova. Type 2 has strong hydrogen lines in the spectrum, and they should. They have a lot of hydrogen in the whole star. All right, and these are formed from massive short-lived stars, whereas the white dwarf supernovae don't necessarily form from the stars may not have been massive. It did not necessarily evolve quickly. So they're very different. And these are found in all types of galaxies. The reason is that it's a star, middling star. But the heavy stars are only, because the heavy stars live so quickly, if the star is not very blue, it's not a star that's suitable to have these type 2 supernova. All right. The total energy exceeds that released by nuclear fusion over the full lifetime of the star. And so we're going to ask the question, where did all this energy come from? How is a supernova capable of generating so much energy? What is going on? Where is all the energy coming from? A very fair question to ask. After all, I told you that there wasn't any energy left. The carbon burned to oxygen, the oxygen burned to neon, et cetera, and all burned to iron, and yet it has all this energy anyhow. Yes? Sorry? Well, it's not a Big Bang. It's very different from Big Bang. And I'll tell you what it is. Just hold on. Okay? This is important for you to understand. A really important topic. It's really the most important topic of the entire course. I want you to understand this. Okay. The energy came from the gravitational binding energy. Remember, I've talked about the binding energy of the sun, the binding energy of the Earth. If you throw a ball up from the Earth, you know what will happen. Energy is taken from it as it climbs out of the Earth. The ball is moving fast and then eventually moves slow. And you have to throw the ball 10 kilometers per second before it has any chance of escaping the Earth. If you try to escape the sun, you have to throw the ball, you have to eject the material at 600 kilometers per second. That is really fast. Really fast. Okay, now, so what I'm saying is that suppose we construct a neutron star out of n neutrons. All right, we put them together. Just pack them together. And I'm going to tell you that the mass of the whole assembly is, if the mass is m, out of each neutron weighs m in isolation. You take a neutron, you measure it on a scale, it measures to be m. All right, you put n together, you'd expect there to be nm mass. But if they're all packed together as a neutron star, that's not right. It turns out that they are 1 minus phi, where phi is the gravitational potential of the matter. The gravitational potential has been attracting them. And this much, you get phi turn out to be about 1/10. And so the remainder, 9/10, is what the thing weighs. It does not weigh as much as you think it does. So you have stolen, remember our equation, E equals mc squared? All right? The mass of the neutron star is not equal to, is not simply the mass of the neutrons in it. It's the binding energy of everything. The binding energy is so strong it amounts to 10% of the mass of everything. Now, what is that relative to? Okay, so 10% of the rest mass has been radiated away. Okay, that's what made everything blow out from the star. Okay, now what that means is that the escape velocity of the neutron star is c times, well, this v over c is square root of phi. And that amounts to 95,000 kilometers a second. Now, that is 1/3 the speed of light. In other words, you ain't going to get off that neutron star if you fall onto one. You're stuck there because you can't generate that kind of velocity through any process we know how to handle. You're stuck. Now let's think about this a little more. All right, so let's ask what the fraction of the binding energy. Suppose you get, here's the equation, 2gm over rc squared. All right, that is dimensionless and represents the energy, the fractional energy of the process. So suppose we have a gas cloud before the sun is made. A gas cloud diffuse in space, and then it collapses. Well, the original density is the original gravitational binding energy is 10 to the minus 9th. That means that the escape speed, which is the escape speed over c squared, is 10 to the minus 9th. Remembering this is the escape speed. All right. And for the sun, it was very small to escape the star when it's just diffuse cloud, 10 to the minus 9th. But when it falls in to make a whole star, the binding energy is large. All right? Now, what is the binding energy of an atom? Suppose you burn hydrogen to form, suppose you burn carbon to form carbon and oxygen, and you form carbon dioxide. What's the binding energy of that molecule? Because carbon and oxygen weighs more than carbon dioxide. There's the binding energy there. What is the binding energy? Anybody? Anybody? Well, it's going to be, the binding energy is going to be roughly 5 electron volts. That's the energy that you need to eject an electron from it. And 5 electron volts compared to a mass that weighs, say, 30 billion electron volts. So say a billion. Just forget the. So in other words, the binding energy is 1 part in a billion. That's this ratio, 10 to the minus 9th. Whereas the energy available when you're on the when you're just on the surface of the sun is 600 kilometers a second, and that represents a binding energy that's much stronger than the energy available in carbon and oxygen. And now if you say, well, suppose we take the sun and squeeze it down to the size of the Earth. The sun was a diameter of 1 million kilometers. Now we're going to squeeze it to a diameter of 10,000 kilometers, or roughly that. A factor of 10 to the 2. And the binding energy will go up a factor of 10 to the 2. Oops, sorry. Here, this goes up a factor of 10 to the 2, from 10 to the minus 6 to 10 to the minus 4th. All right, and the escape velocity becomes very high. It becomes 6,000 kilometers a second. Is the speed you have to have on the surface of that white dwarf to get off. Very fast. Notice numbers are going up. If you talk about getting off a neutron star, it's a very, very dense object compared to a white dwarf. Same equation, but instead of 10 to the minus 4th, it becomes 2/10 or 1/10, something like that. If you talk about getting off a black hole, GM over R squared is 1. That is the definition of a black hole, as we'll see later. In other words, it's you have to give the energy to get off the surface of a black hole is everything. If you're on the surface of a black hole and you start climbing and climbing, you give up all the energy you have, and then you get out. Well, you don't get out. You basically give up all your energy and you're stuck. The photon gets redshifted, 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 it's gone. You don't see it. Whereas a neutron star is pretty close. I mean, it is amazingly close to the escape speed of light. And so its binding energy is there. All right. So this is the progression of binding energy per stage. And remember that the binding energy of carbon and oxygen when they just combine is only 10 to the minus ninth. So these events have enormously larger binding energy than what you can have from a chemical reaction. Enormously. Where did all the energy for a neutron star, how did all the energy get created for the explosion of a supernova? Well, you took something and it had this kind of binding energy, more or less a white dwarf, and you converted it to this binding energy. A huge amount of energy, an energy that is a substantial fraction of the rest mass equivalent, has been converted. You've suddenly made it free. And that is where you get this enormous energy to make these white dwarfs. To make the supernovae remnants, to make the whole thing. Tremendous energies. Now, what you've done is use gravity as the ultimate energy source. Okay. Now, the supernova light curves, this shows the time in days. The massive white star supernova goes like this. The white dwarf supernova peaks a little bit bigger and goes like that, about the same. These processes are argued over and debated and all types of things, and they try to understand why it's exactly this way and not another way. But now they understand pretty much how it works. I'm not going to tell it to you. It doesn't matter for this course. But these are enormously bright objects. They're up to 10 to the 10th luminosity of a star before it blew up. 10 to the 10th luminosity of the sun. That is big. All right, 10 to the 9th some for the other. They are really, really bright. So if one of them goes off and bangs, makes a hell of an explosion, and it's not that far away, like the Crab Nebula is not that far away, you would see it. You can't miss it. It's there. You can see it during the day, just like you can see a full moon in the daylight. This star is so bright that there's no question that the Europeans at the time could see it. Unless they were completely cloudy for a year or two, they would see it. I doubt if they were. And so they only didn't report it because of religious reasons. Okay. All right, now what comes left? You've blown the whole star up. And this thing, the leftover from it is either a neutron star or a black hole. The neutron star, we think that if it's less than 3 solar masses, it can survive. But if it's heavier, it will collapse. It'll have the same process of limitation, that electron degeneracy death that Chandrasekhar talked about. In this case now, the neutrons are providing the degeneracy pressure. They're the things that are moving. There are no electrons anymore. It's all neutrons. All right, so they're very dense. This is like the mass of the sun compressed to something about the size of the Bay Area. You know, put a whole star between us and San Francisco. Nothing to it. There it is, big star. I mean, can you imagine the engineering problem of squeezing a star of 1 million solar masses? I mean, of a few solar masses, squeezing it that hard? Literally impossible, of course, by humans. All right? Now, turns out they rotate very rapidly. They're rotating incredibly rapidly. We'll talk about their rotation in a moment. They have a magnetic field that is stunningly powerful. instead of the half-Gauss field that we have, they have a field measured in 10 to the 12th Gauss, astoundingly powerful magnetic fields. Here is a neutron star. This is one that was observed in 386 AD, and that's the star. Here is remnants of it. This is taken with X-ray satellite. All right. This is the Crab. This is what blew up in the year 1054. Most of it. All right, now the question is, we still haven't asked the question, how does it make, well, I'm running out of time, so we'll go over this next time. But we have not answered the question, how does that star make gold? Where does the gold come from? Because remember, iron was the heaviest element the star could form by equilibrium processes. But yet the star formed gold and uranium and all that heavy stuff. How did that happen? So let's talk about that on Thursday. Okay, and anybody who's curious about me, look it up in the web page of our astronomy department. Okay, good.